Hello, everyone. This is Daniel from ENERZAi, and I'll be leading today's webinar on boosting AI capabilities on Raspberry Pi, focusing on AI inference optimization with Optimium. And to briefly share in prior, Optimium is the AI inference optimization engine that my team is building, and we'll deeply dive into the details in the later part of this session. So first of all, thank you very much for your time today. I guess it will be around 30-minute long webinar for us to introduce about Raspberry Pi AI projects and, of course, our tool called Optimium. And I'll try my best to make this session fruitful as possible. So before we move on, I'd like to briefly introduce myself and my team. And again, I'm Daniel Chang, and I'm the co-founder and CEO of ENERZAi. Our team, ENERZAi, is an AI startup based in Korea. And we are a team specialized in AI inference optimization technology. It's been around 5 years since we started our company, and thankfully, I have the privilege of working with 25 members now, who are the most talented people in Korea. We currently have 28 patents registered and 23 applied, which mostly are related to our core technology, which I'll be mainly introducing today. And based on this technology, we've been accelerated by Samsung Electronics and have partnered with Intel, ARM, Microsoft, and so on. And right before founding ENERZAi, I was involved in one of the fastest growing AI startups in Korea back then, and it was called SwaLab. And during my days with SwaLab, my role was to develop business for a deep learning based machine vision, so basically vision inspection software. And in fact, SwaLab is now part of Nasdaq listed company called Cognex, following its acquisition in 2019. And before that, I worked for SK Telecom, which is the largest telco in Korea. And actually, it was a very meaningful time for me since I've been first exposed to AI technology while developing new business for that company and became an AI enthusiast ever since. Today's agenda is optimizing AI models on Raspberry Pi hardware. I've highlighted here a couple of Raspberry Pi lineups that we mainly deal with, which I believe will be the same for most of the AI developers who are building on top of Raspberry Pi today. So to start with, Raspberry Pi 4 was the single board computer that we mainly focused on when we first started optimizing AI inference on CPU. So processor-wise, it has a quad-core Broadcom CPU, which is based on Cortex A72 architecture, operating at 1.5 gigahertz. Then when Raspberry Pi 5 was released last year, our focus totally shifted to this board for the purpose of testing AI models, since it almost doubled the performance of Raspberry Pi 4. And this model, Raspberry Pi 5, has a quad-core CPU based on Cortex A76 architecture, operating at 2.4 gigahertz. And even though it's slightly more expensive than Raspberry Pi 4, I personally believe it's way worth it for AI projects, considering the performance gain it provides compared to Raspberry Pi 4. And in fact, when our clients consider Raspberry Pi 4 for their AI-powered products, we highly recommend 5 based on our experience testing both. And last but not least, Raspberry Pi released their AI kit this year, which is equipped with 13 to 26 TOPS AI module designed by Halo. And this kit is actually an add-on to Raspberry Pi 5 boards. And this will dramatically provide more options for Raspberry Pi users in terms of AI enablement, especially for computer vision projects. I personally haven't tried out this AI kit yet, but we tested as a team Halo's chips for other AI projects, and we found out that it had way broader coverage in terms of model layers compared to other AI chips, and also powerful performance compared to other AI chips. So I find that very impressive with Halo chips. And as Raspberry Pi hardware are ever evolving as such, I feel that there are more interesting AI projects on Raspberry Pi than ever. I've highlighted here the two of my favorite AI projects on Raspberry Pi, which I could start with the Velo AI's project. So Velo AI is a company building an AI-powered smart bike light and camera called Copilot. So Copilot alerts cyclists to vehicle movements behind them, And they do this with the Raspberry Pi Compute Module 4, along with Halo chip inside this small bike light here on the left. So once it detects overtaking movements of the vehicle behind the cyclists, it sends the information to the connected app, which could be displayed at the biker's mounted smartphone. And also another project which I really enjoyed was finding Wally by integrating computer vision technology into Raspberry Pi. So it's basically, and obviously is a toy project, which was led by a marketing firm called Red Pepper. They trained a classification model with Wally's dataset, as you can see in this picture, and deployed the model on Raspberry Pi board, which was connected to a robot arm and camera. So once the Raspberry Pi powered robot classified Wally among the crowd, it instantly pointed at Wally with its robot arm, which made countless 5-year-olds lose their jobs. So I could name many more interesting AI projects based on Raspberry Pi, but what I believe you would all agree here with me is that it's really hard to find more projects like Copilot compared to the toy robot projects like Where's Wally projects. So then what could be the challenges that's preventing us from building more industrial and commercial projects with Raspberry Pi? One point could be the fact that the recent state-of-the-art AI models are getting larger and more complex as it involves more and more parameters to maximize the model's performance. And this trend could be an obstacle for us to select Raspberry Pi for AI projects, considering that it has a compact resource for embedded use. For the same reason, the processing power might not be sufficient enough for the AI models to meet the real-time requirements, which could be 30 FPS or even up to 60 FPS. And failing to achieve this could be critical to many industrial applications. And of course, the Halo-powered AI kit that I mentioned previously could definitely be a breakthrough for this, but using an AI chip could have its own limitations. So the first limitation could be, due to the nature of newer processors, it might not support some of the layers which comprise your model. In this case, you would have to build your model without that specific layer by sacrificing your time and the model's accuracy itself. But again, Halo's chip was very generous in terms of the layer coverage. And considering that, we could also think about the cost issue here. So adding an AI accelerator could double the cost, which could be a red flag for many commercial projects. So for these reasons, we as a team focus more on how to maximize the performance on CPU platform when dealing with AI projects on Raspberry Pi. And this also will be the main topic throughout today's session. So the first solution for this, we consider applying model compression techniques such as quantization and knowledge distillation or even pruning. And in fact, as a startup specializing in inference optimization, we have very often applied these techniques for not only Raspberry Pi projects, but many other platforms, especially CPU platforms. And the common situation we face here is that for some cases, these approaches might negatively impact the model's accuracy. But more commonly and more importantly, even though these techniques were delicately applied to the AI projects that we've done, in many cases, model compression itself wasn't enough to meet the real-time targets of our projects. And we always needed to find something more to push further after that. So, I mean, after the model compression process. In these cases, a good inference engine framework or an inference backend could come into play. So the most widely used inference framework for AI projects on Raspberry Pi should be TensorFlow-Lite. And for your information, as I've mentioned here in my slide, I found out that TensorFlow-Lite has recently changed its project name to LiteRT recently. And also, you could integrate inference backends like XNMPEG with TensorFlow-Lite, which is a backend comprised of highly optimized network inference operators to achieve further acceleration. And one more interesting project that I could share today is ARM's Cloudy AI project. I'm not sure if you're familiar with it. It's a relatively recent project. I guess it was released like 6 months ago. And this Cloudy AI project goes further than XNMPEG, as ARM open sourced a set of microkernels specifically targeting the architecture which they've designed, which would be obviously ARM CPUs. And I understand that ARM actually collaborated with Google to integrate Cloudy AI and XNMPEG. So once you update to the most recent XNMPEG version, you can enable Cloudy AI for better inference on ARM64. So for this webinar, I've attached some benchmark results, which we've derived to see how Cloudy AI integration impacts XNMPEG performance on ARM. For this, we enabled Cloudy AI on the most recent XNMPEG version and benchmarked against previous XNMPEG version. So the cells highlighted here in yellow are other layers which XNMPEG plus Cloudy AI outperformed the pure XNMPEG version, which, as you can see, applies to most of the layers. So given that Raspberry Pi CPUs are based on ARM64 CPUs, we could say it's worth enabling Cloudy AI once you stick with XNMPEG backend for your AI deployment on Raspberry Pi. However, obviously, there's one inference option which outperforms all the options I've previously mentioned, and it's ENERZAi's one and only Optimium. So to briefly go through the overview of Optimium. Optimium is an AI inference engine, AI inference optimization engine, which we've built on top of our proprietary programming language, which we call Nadia. I won't go into too much of a detail with Nadia for today, but to briefly share, it is basically a programming language that we developed to solely focus on AI inference optimization and AI inference acceleration. So it has a powerful metaprogramming function with it, which enables us to push the inference speed to the model as much as possible. So if you have any, if you're interested in this Nadia project or have any further inquiries regarding Nadia, you can visit our tech blog after this event. I'll be sharing the link through the chat here once we're done today. So to deep dive into Optimium more, to share more details, we could say Optimium is comprised of three main parts, which are graph module and Nadia compiler and runtime module. So we currently take pre-trained PyTorch and TensorFlow Lite models as an input. And once the pre-trained model is ingested into Optimium, we first convert all the layers to Nadia layers so that we could proceed with our unique optimization pipeline. And the graph module then conducts a somewhat high-level or structural analysis automatically on the ingested model, and then automatically finds layer fusion options. So thanks to the powerful language that we have, which is Nadia, we could find many more fusion options than any other tools, which I'm quite proud of. And one of the most distinctive parts of Optimium is that it conducts optimization by connecting the target hardware to Optimium. So for example, once you install Optimium at your local PC, which will be your development environment, and try to optimize your model, which will eventually be deployed on Raspberry Pi 5, that Raspberry Pi 5 will become your target device, and we connect that Raspberry Pi 5 to your local PC and conduct customized optimization on top of the hardware information provided. So to do this, you will have to install Optimium runtime at your target device. So once installed, once this Optimium runtime is installed, it will conduct an interactive optimization based on the runtime execution results, which is profiled repetitively until we go through the entire search space of optimization parameter combinations of layers and come out with the optimal option layer by layer. And obviously, we use Nadia language for this process. So Nadia compiler plays a key role in mediating this entire process. And once this process is over, we'll have an optimized AI model as an output, which is basically an accumulation of highly optimized operators. So word is cheap. So I brought some demo videos here. For both videos, there's some kind of lag here, but please bear with it. So for both videos, the left would be the real-time output of the MediaPipe model deployed on Raspberry Pi using XNMPEG backend. and the videos on the right are the output of using Optimium. And as you can see here, the XNMPEG backend is dropping some frames, which creates some kind of a lag, whereas Optimium output estimates the face, landmarks, and pose successfully real time. So this could emphasize which tool or backend you actually choose to deploy your models on Raspberry Pi could dramatically impact the project's overall performance. And this is a table where we listed models which we optimized and benchmarked against XNMPEG backend. And as you can see, Optimium generally outperformed XNMPEG, sometimes achieving an inference speed which is over 2 times faster than XNMPEG output. So we will be releasing these models listed here at our repository. And I'll share the access point to that repository right before we wrap up today. So it'll be great if you could stay tuned until the end. So finally, I'll just briefly run through a demo on how you could optimize models using Optimium. So the demo scenario is illustrated here in the slide. So I'll use my host PC where Optimium is already installed and remotely connect to the target device, which is Raspberry Pi 5 in this case. So basically, the remote server is pre-installed within our Raspberry Pi 5, which we will be using for today's demo. So I'll stop sharing my screen here. So I think I can. So we'll have some time after we go through this demo. If you have any questions, please be ready and feel free to ask once we're done with the demo. So first, as I mentioned, we have to activate the remote server, which is pre-installed in our Raspberry Pi 5. And just for your information, I have our CTO, Jay, with me today. He'll be helping my demo today. And we have to, so as I mentioned, we have Raspberry Pi here. And I have to share screens right now? No, okay. So we'll activate the remote server, which is installed in the target device, which is Raspberry Pi 5. So we'll copy the address. So bear with me if I have a typo or if I'm typing too slow. It's freezing here in Seoul, Korea right now. So thank you for understanding. So if you see this waiting client connection sign here, it means that you have successfully activated your remote server. So as we activated our remote server, we'll go back to the local PC, so the host PC, where we have already installed Optimium. We have this host PC ready, Optimium ready for now, but I'll mention this again at the later part of my presentation today, but we're currently running a beta of Optimium. So if you apply for your beta, you have a 30-day free trial version sent to you. So we provide that with a license key to you so you can use it for 30 days. And in that case, we'll provide that with you, our documentation, which you can actually go through the installation process. But given that Optimium is already installed here, we'll just start with creating an argument JSON file. So this JSON file will be used for the optimization process of Optimium. So for that, we have to provide some information here. So we'll set a working directory here where all the login, actually the output will be saved. And then we'll import Optimium to start the optimization process. And this process will import Optimium. And then we will create the user argument template here. So it's a very easy step for you to create this JSON file. You will be prompted very kindly. So first, it asks you to create a device name for your target device. So I'll say, and also you will be asked to specify an output directory name, which creates a folder, and the outputs will be saved here in this directory. But if you just skip this step, it will be created as a default, which would be the date time. I'll just skip it. And you are asked to specify the framework of your model. So as I've mentioned, Optimium takes as an input of a pre-trained model. And for this demo, we'll be using a hand landmark light model, which is a TF light model. So we'll say 2. And if your model was a PyTorch model, you should have selected 1. And the prompt asks if your model is post-quantized to float 16 from TF light. And in this case, it's no, because our hand landmark light model is actually a floating point 32 model. So I'll type no. So this prompt implies that we actually take Optimium actually takes floating point 16 models as an input, which to further explain, we also take in-tape models as well. And so the prompt will ask, is your target device remotely connected? So it is remotely connected, as I mentioned. I've activated it in the prior step, so I'll say yes. And it asks an IP address for your remote device. So I'll copy and paste my IP address. And it asks specify remote port of your remote device, and I'll go through this prompt as a default. And the next prompt asks you to specify the architecture of the target device. And in this case, obviously, since our target device is a Raspberry Pi 5 device with Cortex A76 CPU architecture, it will be ARM64. But as I've mentioned previously, if your CPU is an Intel x86 CPU or an AMD 64 CPU, you should have selected 1. And the prompt now asks if your target chip is Cortex M or R. We include this prompt because we don't support R and M for now. We currently support Cortex A among the ARM64 architectures, so we'll select no for this. And if you type in yes for this, the prompt will be terminated. So, and then we select the OS for the target device, which is Linux OS running on our Raspberry Pi 5. So it'll be 1. And then the prompt asks if you would like the Optimium runtime to automatically collect fetch the CPU attributes like such as neon, which our Optimium runtime successfully collects. However, you could also manually specify the desired attributes, but in this case, we recommend typing in yes for the runtime to automatically do the process. And we have to specify the number of threads that we are going to use for inference. So this means that the optimized output model should be using 2 threads here. So we'll type in 2 threads, but you could set it to 1, 2, or 4 based on your target environment. And also it asks to specify optimization log key, and this optimization log key will be used to reactivate the optimization history. So let's say if you have auto-tuned your model previously and want to use that optimization history and then compile after that, you could always use it. So I'll just go with the default for this. And finally, the prompt asks if you would like to enable the hardware-specific auto-tuning, which is very important. So if you are to use Optimium in the near future, based on our beta license, we highly recommend you using auto-tuning because it's the step where the Optimium outputs inference performance is gained the most. But for now, the auto-tuning process takes some amount of a time, so it could take hours for big models. But we are updating Optimium to shorten this step to, in fact, accelerate this auto-tuning process. But for now, it takes a couple of hours for your model to get the optimum output. So again, I highly recommend you using this if you are using Optimium Beta, but I'll just type in no for this. So once we do so, an user argument JSON file has been created. So if I yeah. Okay, so I'll go back to my demo now. So as you can see here, the JSON file has been created, and it includes all the information that I've defined through going through the prompt. So as I've prompted, it says ARM64, which is our Raspberry Pi 5 target, and also it has the number of threads as 2 because I set it to 2, but I'll just fix it. We can always fix it after we give the prompt. We can manually fix the JSON file itself. And also, as for the auto tuning, we can change this false to another value. And everything else, the IP address and the port value has been updated as I've prompted. And now what you have to do is you have to define the input shape and the model path. So as I've mentioned for this demo, we'll be optimizing hand landmark light model. So I'll open a tool called Netron. I believe you will be very familiar with it. So by using tools like Netron, we need to find out the model's input shape. So this is the input node. If you click it, you will have the input shapes for this model. And as I've mentioned, it's a floating point 32 model. So it's mentioned here. And the input shape is as such. So I'll copy this information to Optimium. You should manually update this information. And also, since the model path has to be updated, we will match this to the model that we are about to optimize. So once this is done, I'll save it. And it is saved. So your manual update has been applied. And we go back to the terminal. And we'll import Optimium again. Oh, sorry. Typo. And then once imported, we will start the optimization process. Oops. So this is the JSON file that we oops, thank you. So this is the file, the JSON file name that we just created and manually updated. So it will ask you for a license key. So if you apply for the beta for Optimium, we will provide you with a license key that will be activated for 30 days. So you could try with your own models and with your own hardware. So once we type in our license key, the optimization process will be activated. So as I mentioned, we turned off auto tuning, but we highly recommend you actually pursue the auto tuning process because that's where all the performance gain happens. But for the sake of today's demo, I've disabled it. And while the model is being optimized besides the auto tuning process, I'll just briefly share some information about Optimium current status. So currently, we're running a beta of Optimium, and we have a limited coverage for inference optimization. So model-wise, we only support convolutional models for now. So basically CNN models. And also architecture-wise, we only support CPUs, and that will be x86 CPUs and ARM64 CPUs. But however, we do have plans to expand further. So hardware-wise, we are planning to expand to CUDA-based GPUs, CUDA GPUs, early next year. And also earlier than that, we have plans to expand to like transformer-based generative AI models, including language models and maybe diffusion models and so on. So we'll after this webinar, we'll have you updated with this information regarding our coverage or any beta beta plan or roadmaps and so on. So yes, since we disabled auto tuning, the entire optimization process has been done. But for the sake of the live demo, we actually prepared an already auto-tuned, which means already optimized hand landmark model. So I'll use that auto-tuned model for the live demo today. And for that demo, I'll just stop sharing my screen, and I'll hand over the camera to Jay. So Jay will be live streaming the live demo of the Optimium optimized output. So he's showing the Raspberry Pi 5 board, which we used as a target device to optimize the model by using Optimium. And actually, we'll be running the XNMPEG backend model and the Optimium optimized model, the two models on that device, and show you live right now. So we'll start with a live demonstration first. So as you can see here, it's the FPS for the XNMPEG. It says Tensible Lite, but we activated the XNMPEG for that. So it shows that it says that it has like 20 FPS in terms of inference speed. So you can see there's kind of a lag here. And oops. So but we'll turn on Optimium optimized output on Raspberry Pi. And you can see the FPS is slightly faster, which actually dropped by like 3 FPS before compared to what we prepared. And we turn on Tensible Lite. You can see the lag difference here. So, and Optimium. So it's so improvement itself would be around like 50% improvement in terms of inference speed and Tensible Lite. Yeah, so I think it would be better for us to record a video and then apply these two models and concat the video and show the output for comparison. So I'll just start recording a video. And then start recording. And then first we will process this video with XNMPEG backend model, and then we'll process this same video with an Optimium optimized model. And then we'll compare these two videos by concatenating the output. So again, whereas Optimium output shows around 30 FPS inference speed, you can see that the XNMPEG backend output is around 20 FPS. So we could say there was a 50% improvement in terms of inference speed. And as you can see in this output, the XNMPEG backend drops more frames compared to Optimium optimized output, which might be critical for mission critical applications such as autonomous driving or driver monitoring system and so on. So which means that the inference backend that you use might be critical for your AI-powered application or devices and so on. So that was a very short demo. And in fact, we will share all these Optimium pre-optimized models through our GitHub repository. So please visit and maybe start our repository. So I'll share my screen again to get back to the slides. Yes. So, as mentioned, and again, we just opened a GitHub repository to share all the listed MediaPipe models that are already optimized from our side using Optimium. So, along with the Optimium runtime, which actually could execute those models with. And we're actually planning to release more Optimium optimized models on this repository. So feel free to let us know which models and target hardware you would like us to optimize at the discussion section of this repository. And if anyone here today is involved in any kind of Raspberry Pi community, please kindly share this information with your members. And to share some more background, Optimium, again, is running a beta, so you can sign up for the free trial beta. And it is actually, the beta link is actually included in this repository, so you can find out via this QR code or this link. And I've also updated the tech blog links and also the some demo videos and also team websites where you can find more information about our technology at the GitHub repository. So it'll be great if you could visit after this webinar today. So to sum up, we are currently helping a number of companies here in Korea who are seriously considering Raspberry Pi for the mass production of their AI-powered products. And these companies are involved in robotics or smart parking solution, healthcare, and more. And we are closely working with them based on Optimium so that they can meet their mass production target with us. And our goal is to foster a lot of commercial and industrial AI projects on Raspberry Pi by using Optimium. And I'll be more than happy if you could be part of it. So this is all what I've prepared for today. And it'll be great if we could spend the rest of our time answering your questions if you have any. So I'll activate all the microphones so you can perhaps ask through a voice through by activating your microphone, or you can just ask questions through chat.
Hi, this is Irene, and thanks for the talk today. I just have one quick question. As you mentioned earlier, that Optimium takes float 16 models. So does Optimium provide quantization functions?
So Optimium itself, thank you for a good question. Optimium now does not support quantization itself. Rather, it takes pre-quantized models as an input, as I've mentioned. So that's why we prompted if the model is float 16. It didn't ask if it's int 8, but we do take int 8 models. So to answer your questions, we don't quantize the models within Optimium, but we go further after that. So we take quantized models to make it faster and work more efficiently.
Thank you.
So anyone else have any questions? So if not, just feel free to visit our repository and leave your questions there. And also feel free to visit and download the models and enjoy it on your Raspberry Pi projects. And as I've mentioned, it would be great if you could, suggest some ideas on which model for us to optimize on that repository as well. And besides the repository itself, you can always visit ENERZAi website and contact us through the contact email provided at that website. If you have any inquiries, if you need any consultation, or if you need any help in accelerating your AI models on CPU architecture for now, and GPU architecture in the near future, we'll be more than happy to help you out. So if there are no more questions. Again, thank you very much for your time today. And I hope it was a fruitful session for you to understand how to run AI models on Raspberry Pi or catch concept about Optimium. And it'll be great if you sign up for beta so that we can follow up and make your AI models run faster. So thanks, everyone. Thank you for your time. And I hope to see you soon again.